Uh, Buenos días a todo el mundo. Si se recomienda poner los móviles en silencio o directamente apagarlos. Welcome everybody. It would be good to switch off the mobile phones or just to put them in mute mode. I'm Emilio Hernández García. I will chair this committee for the thesis defense of Alejandro Almodóvar. The thesis has been supervised by Tobias Gala and Cristobal López. Let me introduce also the other members of the committee. Luis Angeluta, she comes from the University of Oslo, and Ricardo Martinez, who is coming from the Center for Advanced Systems Understanding in Görlitz, Germany. Okay, Alejandro, you are expected to spend less than an hour in your presentation, and after this we will make our questions. Okay? Go ahead.
Hello to everyone to come, and thank you to the committee to come. And I present my thesis entitled like Interacting Particle Systems with Mobility and Demographic Dynamics as Biological Models. This presentation will have different parts. First of all, will be a brief introduction. I will explain what is proliferation matter. Later on, I will explain my model and the model that we explain on all the thesis. And the main part will be present the main result of my thesis. This result have three different parts and three different cases. And finally, we present a final remarks on my thesis. Then we begin explaining what is proliferation acting matter. Proliferating active matter refers to systems that move, consume energy, but also multiply and die. This kind of system can go from very small systems like bacteria to large systems like tissues, birds, or buffaloes. Okay, about proliferation antimatter has also been studied. There are a lot of material about active matter and a lot of material on proliferation antimatter, but we want to combine both topics in our thesis. Studies about active matter are related with how it arises the motility, what dominate in the interaction about the organism, or for example, when the orderly states emerge, and study the phase transition of these systems, or how much energy is consumed, or for example, what we learn to make a robot. This kind of different topics on active matter. For example, we have some examples here. For example, the study of phase diagrams for material swarming, or for example, the study of social interaction of free ants. On the other part, we have studies about proliferating particles, where we study the population dynamics, how growth invasion, the growth fronts evolves, how demographic influence the density equation, or how the environment affects the selection of the species. A study of this can be, for example, this study on birds and on Malthusian flocks, or this study on young about reproductive pairs or correlation of organisms. Then, now we are interested on proliferating active matters. Why? Because in this study of matters, they assume that the number of particles is fixed. They ignore that the living units are born and die. This proliferation is important because protects conservation of the number of particles, inject mass, and defects, and determines who wins or coexists on an ecosystem. It's clear that not always is important, but for example, if the study time is shorter than the cell double time, for example, studies on swimming behavior bacteria or the study of qualitative behavior of flock of birds, the proliferation is not an important topic that's interesting when we study this kind of systems. But for example, it's important if in some biological or ecological cases, for example, if you want to study how bacteria form biofilms over days or how tissues will become tumors, the proliferation is very important. Now, I'm going to present the simple model of active matter on which my thesis is based. Later on, I will include some kind of proliferation. In this thesis, we adopt the AVP model. That this model we present the beginning in this paper on Marchetti, and we use this model that is a minimal powerful approach. In this system, the particles have size and are circular. They move with nearly constant speed, And in all these tests, we work in a two-dimensional space. The interaction between the organism is only via volume exclusion, it depends on the size. And due to the simplicity, this model is very used for benchmark for investigation emission behavior in different systems. The novelty on my thesis is that we combine the active particle, the particle that self-propels, with the Birdseye dynamics. Here we can, a simple examples what happens in a sample system, that the particle begin to reproduce until they fill the system. The particle move and reproduce until they fill the system. Okay, now I'm going to present my model. This is the core of my model, and then we will add different ingredients. This model has three components. The first two is the moment and the size that is simulated via the Langevin equation. And the third part is the Birdseye dynamics that is simulated via Gillespie algorithm. Now we are going to present the Langevin equation, for example, for the E particles for a collection of N Brownian particles. Important, we are in the overdamper limit. This means that the initial terms can be neglected, that the moment is measured from the inertia. Then the Langevin equation, we have different parts. The first part is the force that comes from the to simulate the size, that is simulated via Lennard-Jones potential. In our case, the particles have a diameter sigma. The second part is the Brownian part, that is, this comes from the thermal fluctuations, where D is the diffusion constant and D is the Gaussian noise. And the last part is the self-propulsion. Later on, we will talk about this. If we go to the other part, the Birdseye dynamics, we say that the particles can reproduce and die, then the number of particles change over time. The death events occur through a Poisson process with a constant rate delta, but the bursts are more elaborate. At the death events, the bursts are treated with a rate, that in this case is beta, but the burst events only go ahead if there is room for the spring. Later on, we will explain better how the Birdseye dynamic works. Then go again from this part. We say that this is the self-propulsion. When this force is zero, we talk about passive Brownian particles, and when this force is different from zero, we are talking about active Brownian particles. How is this force? This force is just a constant modulus and a direction. This direction changes over time in a diffusivity term. This is rotational diffusion, and this is Gaussian noise. Okay. Then now we'll talk about how works the Birdseye dynamics. We say that the particles reproduce under the no-board particle is located close to the parents. For example, if these particles try to reproduce, we try to reproduce in any of these places. And among all the positions, we choose only that they are not overlapping with other particles of the system. When I choose is random between all the possible ones. And if there is no space, there is no reproduction. And the events occur or the production or non-production, the simulation continues. Here we have a movie of what happens. For example, if we choose these particles to reproduce between all the this position, the blue is that the particles can place, and the green that they are overlapping. We delete the green. About the blues, we choose one at random. If, for example, the number particle is located here, and the simulation continues. Then we present the main result. This presentation will have two different parts. On the first part, I talk about structural phases determined by stochastic bursts and death events. All this work can be found in this publication. On the second part of talk, we will talk about extinction and coexistence in a binary mixture. The work we will present in this paper. And the last part, we will include a game theoretical like interaction, and this work can be found in this paper archive. Then let's go to the first part. What we want to do? We want to construct the full phase diagram on active Brownian particles, but including the proliferation. Then that's the question that we ask is how the dynamics of ABP, active Brownian particles, change within our parameters with the Birdseye dynamics, and how the phase diagram change. Then, first of all, to construct the phase diagram, we are talking about structural phases. What is structural phases? Structural phases is just how are the spatial order. The system can be in a liquid, static, or solid, depending on the order. In a system of very periodic structure, we are in the order phase that is called crystal or solid, and we begin to this order. We go to solid to liquid, going through a static phase. Okay, to determine the phases, we use topical defects. Defects in a crystal refer to deviation for the ideal arrangement in a two-dimensional case. That is what are we working. The ideal arrangement is the triangular lattice. That means that each particle has 6 neighbors due to the hexagonal symmetry. Okay, and if the particles have more fewer than 6 neighbors, they call defects. And these defects is important, but because we can determine the phase and the lattice properties. Here we construct an example to determine the phase. We construct a Voronoi diagram where we have different cells. The white cells, there are cells that have 6 neighbors, and the blue have 8 neighbors, and the 7 neighbors, sorry, and the reds have 5 neighbors. And 2 kinds of defects that we can find are, in this case, disclination, that is a single defect with 5 or a single defect, and dislocation, a pair of two defects that one have 5 neighbors and the other one have 7 neighbors. These are 2 kinds of defects. There are a lot of more about the defects. Then now we can go. Then we say that we can construct the phase diagram with proliferation. First of all, we are talking about what happens without proliferation. This is the phase diagram without proliferation that is made by Di Gregorio. That depending that this goes to the packing fraction, that the packing fraction is just the space occupied by one particle multiplied the number of particles, then it's the space occupied by the total number of particles. And here we have the Peclet number, that is just a constant, the size at temperature multiplied by the active force, that is the velocity of the particles. And we say that this transition in this case is driven by activity. We observe that increasing the density, we can go from solid to liquid to solid, and increasing the activity, we can go from solid to liquid. Also, we have here another phase that is called MIPS. Later on, we will talk about this. That is just a coexistence phase where we have dilute and then phase. Later on, we will talk more about this. Then we can construct the phase diagrams. This is the phase diagram without proliferation, and what happens when proliferation is included. First of all, remember that the burst event occurs only when there is empty space to can reproduce, and we will work only on the part that when the burst rate is greater than the death rate, because in other case, if the death rate is bigger, the number of deaths is greater than the burst, and the number of particles finally we will 0, and we have no particles. Then we expect that the number of particles grows until fill the system, and we observe here the number of particles over time from different burst rate, fixing the death rate, that increasing the burst rate, we increase the number of particles. In the first beginning, we saw that the number of particles will be independent of the burst rate, but not. We observe that the number of particles depends on the higher number of burst rate. Also, in this part of this stationary, it's not really stationary because the number of particles change. In the meantime, we observe that a balance between the death and the burst. Okay, now we characterize the different phases. First of all, we will distinguish between passive and active particles. And as we observed before, change the number of particles, which we produce a transition from liquid to solid, then we expect that change the parameter of burst and death. Also, we induce similar transition as before. Then here we have different snapshot of the system. Here in a low burst rate, we said that in system in a liquid phase, and increasing the burst rate, we go from static to solid. Below, we have the Voronoi diagram where we can observe the defects. The green cells that are 6 neighbors, then we are the cells that are orange or blue are the defects. In this case, we obtain more defects than in case without proliferation, comparing 2 systems with the similar number of particles. Also, in the solid phase, we observe a small number of defects, as we expect. But one can say that there are a lot of defects to be a solid phase, but what happens is that almost all the defects are vacancy in the solid phase. I mean that we remember that the particles reproduce, but also die. Then, when we are in a perfect alignment, if one particle dies, we produce a vacancy, that is a missing particle, and this produces a defect. But it's just that this space will be fast occupied by a particle that reproduces. Then, now construct the phi diagram with passive Brownian particle with proliferation, and this is what obtained. We draw the birth rate in front of the death rate. This black part is the part. First of all, we construct the phi diagram with different parameters comparing with the ABP. Here we have the birth and the death rate, the rate of the demographics, comparing with the number of particles on the standard ABP. And we have different parts. The black zone is the part where we have no particle in a large time because the death rate is larger than the birth rate. When the birth rate is very large compared with the death rate, we are in a solid phase, that is this gray zone. When the birth rate is a little higher than the death rate, we are in a liquid phase, that is the blue zone. And between the two phases, we found the static phase, that is this small, very small orange zone. And all these general features are maintained as we vary the size of the system. Now we construct the phase in front of the birth rate. Here we have, for different value of delta, if we fix one value, any value of delta, any value of the death rate, we see clearly the two regimes. The blue is the liquid, the orange the static, and the gray is the solid. And increasing the birth rate, we can go that the defects decrease, but we can observe that in the static phase, the decrease is rather sharp than the other transitions. And also the transition obtained here is with a very high number of defects compared with the standard one, that the standard one, the transition is around 5% of defects. Here we observe that the transition is around 20%. Now we go to the active Brownian particles. Then we observe that the birth rate changed the number of particles, but in this case, also the same proportion determines the number of particles. We go through the packing fraction that we say that it's just the pi occupied by particles, that is a constant multiplied by the number of particles, and on time. And we observe that increasing the cell proportion, we increase the number of particles. Then we have another parameter to construct the phi diagram. And we say. Then now I will talk about a phenomenon that appears on active Brownian particle also with a proliferation, that is MIPS, that is motility in the phase separation, that we have a separation of dilute and dense phase. Here we observe clearly that we have a part that is very dense and one part that is very dilute. And this proves due to the activity, that the collision with the particles due to activity produce that they slow them in areas high density, and this cluster grows and new particles can collide with this cluster, and this produces a positive feedback, producing that this very high cluster of dense particles. Here we have a movie in our model of proliferation particles. And what can observe? Initially we have a few particles, the particle begin to reproduce until we reach a point that we begin to construct small clusters, and we have a very big cluster. The black points are the points that are reproducing. Then we observe that the reproduction is almost on the dilute phase or in the edges of the cluster, because in the middle of the dense phase it's impossible to reproduce due to the high density and the very small space. Now we're going to go through the phase diagram from active Brownian particle with proliferation. Here we have the cell proportion velocity in front of the birth rate. Well, we're less than the birth rate. And we say that for low activity, the system behaves broadly as a sensor activity. But when we go from large activity, that we remember that activity produces that particle aggregation, we have interintervals. Comparing with the ABP without proliferation, we set here a new part that we not end there. We were in a very high birth rate, we can go increasing the activity, we can go from solid to static to liquid, but we can have a reentrant phase that is the static phase. This static reentrant static phase is produced because when we produce high activity, the particles aggregate in a, how we say, MIPS, and we have a very dense phase and then dilute phase. And in the dilute phase, we have free space, and in our model, free space means particles can reproduce. Then more space for reproduction, this space is occupied by more particles, and the number of particles grows a lot. And due to the high number of particles and this high density, we prove that the system begins to order a little bit, and we go to a reentrant static phase. Now we are going to do a summary of this first part. We remember that we have used a model with main particles to which we include the dynamics of bursts and death. We are considered bursts are antiparticles. When bursts dominate over death, the choice of parameters determine the structural phase. For active particles, also the subproportion determines the number of particles. And in general, due to demographic, the number of defects is larger than in the standard one. Standard case, remember, we refer to this case without propagation. And also, for large activity, we say that the static phase dominates, reflecting the presence of defects due to the combined effect of demographic and activity. Now, let's pass to the second part, where we are working on extinction of coexistence in a Bayesian mixture. Here, we use the same previous model, but here we have two types of particles. And this is not very realistic in biological application, because in biological applications, there is a distribution outside, but a first approximation can be considered two types of particles. This kind of type of particle means different sizes. That one is bigger than the other one. To remember the size, the green ones are the bigger ones, and the red are the smaller ones. Because maybe in the movies they are not see which is bigger. And the question we ask is, can both particles coexist, or under what conditions and what parameters help long-term survival? We will observe that depending on the birth rate and diffusion activity, we can reach coexistence. Okay, the model is the same as before, but with different sizes. We have an index S for the small particles and index L for the large particles. The total number of particles is the number of particles of large particles plus the number of particles of small particles. We see that the diameter of the large particles will be bigger than the diameter of the small particles. The Langevin equation is the same, but the diffusion, it depends on the type of particle. And now we will talk in two cases. The first case that we work is that we use different burst rate from large and small particles, but we use passive particles, meaning that the velocity is 0. And the second case, we use the same burst rate from both types of particles, but different velocity of both types of particles. In both cases, we use the same death rate, but both particles have the same diffusion constant. We made this because in the first case, we want to observe that with the burst rates, we can reach coexistence, only changing these parameters. And in the second case, fixing all the same parameters from both types of particles, only changing the activity, we can observe if we can reach the coexistence. Let's go to the case one. This is based on burst rate. We said that here we construct a diagram where we have the burst rate of the small particles in front of the burst rate of the large particles, and the colors means the fraction of small particles. Means that if it's red, one means that all the space is occupied by a small particle, and the green part means that all the space is occupied by green particles, and the colors in between is that they are coexistence. As we expect, when both burst rates are the same, we only have small particles because the large particles have a disadvantage to do the space availability, and it's difficult to reproduce them. When the burst rates are the same for both, we have only small particles. If we increase the burst rate on the large particle, fixing in this work the burst rate on the small particles, we have reached coexistence. That it means this yellow zone. Here we see a movie that we will say that both particles coexist, and means a lot. And we increase a bit more then the birth rate of the large particle, we can reach that the system is fully dominated by the large particles. Then let's talk about activity. In this case, we use the same birth rate and diffusivity for both particles. And here we go to the phase diagram from the velocity of the small particles in front of the velocity of the large particles. As before, we go through the colors depend on the fraction of the small particles. When the velocity of the small particles is small, we only observe that small particles dominate or coexistence, large particles never dominate. But when the velocity of small particles is higher, we observe interesting results. For example, if we see the velocity of small particle, where in this region, the small particles can form MIPS, and the large particles form MIPS, depending on the velocity. In this case of a small velocity of the large particles, for example, in this part, we reach a coexistence that the particles coexist on both sides. If we increase a little bit, we reach a region where large particles dominate. But we see that at the beginning there are both particles, but in a large time, we observe that only green particles dominate the full system. If we increase a little bit the velocity of the large particles, we can reach again a region of coexistence. Here we can observe that both particles coexist in a long time. And if we increase a little bit more, we can reach that only small particles dominate the full system. Important that in the case of coexistence, both particles present the same particle distribution. Now, I'm going to present the summary of this part. We use a model with moving particle and Bose-Einstein dynamics with only two different particle size. We can reach coexistence by varying birth rate. Also diffusivity, but by the time I don't show in this presentation, but we can find in the thesis on the paper. And we also said that also we can reach coexistence varying the activity. Also, we all said that varying the birth rate, large particles can dominate, but in the case of active particles, in the case of low activity on the small particles, large particles never dominate. And in the case of higher velocity of the small particle, when in the region that these particles can form it, depending on the velocity of the large particles, we have large particle domination, small particle domination, or coexistence. Now, go to the third part and the last one, where we include again theoretical-like interaction. Important. This use the initial model, means that all the particles have the same size. Is this from the initial model? Okay, we include again theoretical type of interaction between two types of particle population. What it means, we have two types of particles, particle A and particle B, and the growth rate is influenced by the particle type of the surrounding. This is very used in ecological and evolutionary games, where competition and cooperation are key drivers of population dynamics. Also, this theory has been vividly used in social and ecological. For example, in a typical social system, each individual plays a certain strategy and receives a reward from interaction with other individuals. Or in the case of biology, we have two species and these species cooperate or coexist. Okay, then we present the model. The model is the same as the beginning. They have the Langevin equation, but the diffusion depends on the type of particle and the number of particles, the sum of the both type of particle. The death rate from both type of particle is the same, but the birth rate we have a constant and designing the payoff. Now we talk about this payoff, and the X means that it's tape A or tape B. Okay. First of all, beta 0 is greater than delta to ensure that the birth rate is always larger than the death rate. And this payoff is this kind of, we use this payoff with the payoff, for example, in this case, we have this particle within a radius. We compute the number of particles within the radius. For example, if it's type A, we compute the number of particles of type A multiplied by a constant plus the number of particles within this radius of type B within multiplied by a constant. The same for the type B particles. And the parameters A, B, C, D are the parameters of our model and can be positive or negative. And we can reach different outcomes. We can reach coexistence, stability, or dominance. Now we talk about what means each outcome. And combining the special constraint on percentage, activity, and Gestalt-like interaction, we can explore how localistic competition and cooperation influence the population dynamics. We talk about the three different outcomes. In the coexistence, population of both types can coexist in stable proportions. In the stability case, depending on the initial condition, either type B or type A will eventually vanish. And in the case domination, we will focus on the first type, it's the same. We focus on the type B domination, that in the case, type B dominate always the system independent on the initial condition. Let's go to the consistent part. We use this metric where A is negative, and then, for example, the type A particle, the reward is positive when it's surrounded by more B particles. Because remember, I negative that the birth rate of A particles is greater when it's surrounded by B particles. Then we expect a mixture scenario. Then here we compute the percentage of particles of the same type surrounding by a given radius. I mean that depending on this tension stress, we compute how the percentage of the same type around one particle. I mean that we will say one particle and how many are the type B surrounding this particle, and how many particles are the type B surrounding this particle. And we will say that increasing this interaction, the particle become more mixed. Means that reach the 50% means that 50% of the particle are type A and 50% is the type B. And when interaction is 0, we have that the system is more surrounded by the same type of particle. Now we say the same, but with the velocity, also we observe that increasing the velocity, also the system mix. That means that here we observe a case that we initially begin with 3 particles of each type. Here we have very high velocity. Then we have in this zone, and we observe that the particles reproduce, and the particle due to velocity, the particle meets a lot, and we said these are typical results in this region. And we also said that increasing the interaction will increase the mixing. Now we go to the B-stability case. We use the same metric, but in this case, A is positive. Then in this case, in opposite to the consistent part, particles tend to cluster with the same type of particle. Then we have a scenario to observe what happens. Initially, we have few particles each one. Here we have how the number of particles evolve over time. We observe that the system fills very fast the system and consists in a long time, but eventually there is no coexistence a long time. Also, we observe that, for expect, in the transient, we observe that a particle segregation, that the type B particle can be with the type B particle and each type can be with at the same time. But we say that in long time there is no coexistence, and with change the different parameters only made that we change the extinction time, the time to reach this extinction. But always there is one particle that extinct. Only one particle survives. Now we go to the domination case. In this case, we use that the type A particles have no reward depending on the surrounding. Then the birth rate is constant, and the B particles have a payoff. And we ensure that the birth rate of the B particles is also larger than the birth rate of the A particles. So in this case, we have type B domination. Here we say a simple scenario. So we see that the type A can grow, but the domination of the birth can make that the extinction of the type A particles. We can read that finally the A is extinct. Now we do an experiment where we'll say that, okay, we have a lot of A particles. We introduce only one type B particle. These two kinds of systems, these two types of particles can survive and coexist, or this new particle I want introduce will eventually die. Okay, here we have a system of only a particle. We introduce one B particle, and this particle can die, but also can reproduce. If it reproduce, we make that the full system coexists. Now we compute the probability that we see coexistence, including one particle, two particles, or three particles. In the case of introducing different particles, increasing the interaction strength, we make that the probability grows. And also we observe that including only one particle at a very high interaction, we only reach around 55% of reach coexistence. This is due to including only one particle. This particle can die. Then in some time, these particles will eventually vanish. But including two or three particles in the high interaction, we reach that almost 100% of reach coexistence. We remember I is negative in the case of coexistence, and the particles surrounded by the opposite type experience an increase of the birth rate. When we include only one type B particle surrounded by full of A particle, the birth rate of this particle is very high compared with the other particle, and the probability to reproduce is very high. And we say that increasing the interaction, the probability increase. Now we make the same, but in the case of domination, and in this case, we expect the new particles that we introduce dominate the full system of the extinction of the new this kind of particle. We compute here the probability that dominates on the type B particle in front of the interaction strength. In this case, we have the parameter C. Variant, also the velocity. We observe that also increasing the interaction will increase the probability, but increasing the velocity, the probability decrease. This yellow line is the theoretical theoretical result that we obtain, but by time we don't show here, but we show that fits very well with the case with a velocity. The computation can be observed in the thesis. And now we make a summary of this part. We have used the model with moving particles and Bertel dynamics, but including, again, theoretical interaction. In the case of coexistence, we observe that a strong interaction activity enhances mixing, and particles are surrounded by the other type of particle. In the case of stability, particles tend to cluster of the same type, leading to segregations, and there is no coexistence in a long time. And in the case of dominance, only one type always dominates the full system. Then now we make a conclusion of the full thesis. We remember, we make a model of collective dynamics in system of proliferation module particles using individual-based model. We explore how stochastic birthday process, binary mixture, and gas theoretical interaction influence the structural phase and the collective behaviors. In the first part, we construct a detailed phase diagram to the mass transition between liquids, static, and solid, and as a function of the activity and the birth rate. Of the second part, to extend this model to a binary mixture with different sizes, resulting in showing that change the diffusion activity of the birth rate, we can reach coexistence or dominance. And finally, on the third part, we introduce again theoretical interaction to model cooperation and competition. And we show that we can check structure, coexistence, and the collaboration with different parameters. Now, we can show that how this work can do in the future work with this model. For example, we can include polydispersity and non-circular shape. For example, more cells, viruses, and bacteria are not circular, then we can include a polydispersion to different sizes or shape. Also, if you know that polydispersity in size and shape perturb the equilibrium phase diagram, then with different sizes we have different phase diagram. It is known in this paper that a small very dispersion delay the static ordering and thins out the MIPS window. And also, maybe if the birth death dynamics could reveal different nematics textures that is on table with different models. A way to implement this, for example, in the model is that the size is to implement with the distribution of sizes, affirm the shapes with an orientation vector, and using, for example, again, burn potential for collision to implement this. Another kind of system that we can implement to the model is, for example, including machine learning in particles, that is this kind of particles called smart matter, that we can design agents that learn to maximize the reproduction success or avoid bottlenecks. We can test if agents can learn to slow down in overcrowded zones, or for example, in the case of MIPS, that the particles don't collide with the MIPS and slow down to increase the probability of reproduction of this information, and this learning can be transferred into microrobot or cell culture with autogenic control. And way to implement it, for example, that each particle observes the local density or the defects, and depending on what observed, we win a reward, for example, depending on the next row, and that we have reward with the next row, but less than the collisions. Or another kind of implementation is that we observe and in that this kind of particle want to increase the structural order, and depending on this structural order, we have a division or another one. And another last part to do with this model, for example, including non-reciprocal interactions. It is known that non-reciprocal interactions break fundamental symmetry and generate rich patterns. Also, this non-reciprocal interaction is known that destroy MIPS and can pair oscillating clusters. And sometimes this non-reciprocal interaction is used to phage therapy, or microbial biocontrol as a predator-prey relationship. A way to implement this predator-prey interaction is, for example, that one type of particle have an attractive force from the other type of particle that have a repulsive force for one, and if the two types of particles overlap, the particles die. Or, for example, that the particles A apply a torque to one target B, and the B can escape from these particles, the other one, and the particle A earns a reward and reduce the distance. This is kind of work that we can complement with my thesis and work on the future. And this is all, and thank you for your attention.
Thank you, Alejandro. So now is the turn for the committee to ask you questions. Before that, if someone wants to leave the room, this is a good moment in order to avoid stopping the presentation or the questions later. But of course, everyone is welcome to remain if they want. Ahora vamos a empezar las preguntas y bueno, si alguien quiere